Right. Let's look at 2, 3, and 4 first, and then take a look at 5. So okay, so 2, 3, and 4 are basically all building up the same function. So let's look through the pieces of what that would look like. Okay, so here I've got a function, and the idea was that if I want to set a function where I can either set all the values below some cutoff to that cutoff or set all the values above some cutoff to that cutoff. So I'm going to decide that, okay, the input arguments in this case are going to be the vector of values that I want to operate on, and then I'm going to allow the user to set what the threshold is, and I'm going to set a default value for that threshold, but the user could change that. And then I'm going to basically have this toggle switch that's either going to be true or false that says, am I operating on the values above the cutoff or am I operating on the values below the cutoff? So this would allow this function to behave in 2 different ways depending on this flag that the user chose. This is an example of, I could write one function that only operates on values above a cutoff, and I could write a separate function that operates on values below the cutoff, and that would be fine. That would be sort of fairly modular. But in this case, it also feels like it makes sense to combine those 2 ideas into one, because this idea of thresholding is sort of the same thing. It's just whether I'm doing above or below. It's sort of doing similar operations. And then all I'm doing here is I'm just using an if statement to decide which of the 2 conditions, the below or the above situation I'm in, and then I'm just going in and using my vectorized subsetting and assignment in the ways that we saw in the modules yesterday, and then I'm returning x as the output, again, because modifying x in the function here doesn't change whatever was passed in as the input into the function in the context of being outside of after the function finishes.
Isn't if x is bigger than the threshold, it should return x? Because the question said if it's below, it returns a value.
Set any value below the threshold to be the value of the threshold. So did I not solve my own problem? Is that what happened here? I'm saying for any x's where x is less than the threshold, set it to be the threshold. I think that's doing what I said.
If it's bigger, it return x. If it's bigger than the threshold.
Oh, right. That's for the x's that are bigger, they're not going to be affected by this because this is only modifying the ones that are less than where the stuff in blue is true. Okay. If I have x gets c of 1, 3, 5, and then I say x of x less than 4 gets 0, and then I look at x, the 5 still stays the same. So the ones where the index ends up being false is not affected. Okay, so then, yes?
Instead of having to rewrite the whole line, you've just somehow chosen whether you want a less than or greater than operator, and then use that same operator. Because you can make the operator a variable.
Yeah, I could have done that. I think that's a little beyond the scope of what I want to talk through here, but I could do that because operators are just functions, and I could have done some trickery with that. Yes. Okay, so then the third one was okay. Now augment this so I check if the input is a numeric vector and return an error if not. So this is starting to get to, as you start to write functions, you want them to be robust such that if a user gives a garbage input, you don't just create an error where it's unclear what happened, and you don't just proceed along and give a result that's bogus. This is harder in R than in some languages, like compiled languages like C, because you set up a function. There's nothing, you expect the user to give you a numeric input vector, for example. There's nothing to stop the user from passing in a data frame or a set of character strings or a list or anything else. So there's sort of no control over what you get passed into your function. So if you're really going to be robust, you actually end up having to write a lot of sort of tedious code of checking to make sure that the inputs that the user gives you are what you're expecting and what your function is able to handle correctly when it operates. So it's usually hard to be truly robust with that, but you can at least try and do some to catch the sort of common errors that might occur in terms of what the user passes as an input. So now all I'm doing is I'm modifying the function so there's an initial if statement that just checks, is x a numeric vector or is it a list? Is x not a numeric vector? There's an exclamation point hidden in here that I didn't see initially. If it's not a numeric vector or if it is a list, just say, I do not handle that in this particular kind of functionality that I'm writing in this function. So I'm just going to call the stop function. This is then going to return an error back to the user, and the error message is going to say the x must be a numeric vector. So it tells the user why this fails. If you just in other cases, you might want to print a warning, and you've already seen a bunch of functions where you'll do something and R wasn't expecting you to do it quite that way, and you got back a warning. You could instead, for example, use the warning function and create a warning instead and still continue onwards. In this case, it makes more sense to just stop with an error, but in other cases, it might make more sense to have a warning. Questions here? And then I guess I guess I don't have an answer to the fourth problem here. Okay, I have no answer to 4, and I called the answer to 5 number 4. Maybe I won't. This is not all that common that you use this, so I'll leave this. That if you're interested in it, you could look at it on your own. And there are some good examples in the help for the invisible function of how it works. Okay, so then one of you asked about number 5, which is in here labeled number 4. So let's change that. So I have my column sort function. This is the original column sort function where I only allow sorting based on 2 columns. So that's not all that flexible because we could want to sort on more than 2 columns. So I said a little bit about the ... function. And so here I'm going to set up my second input argument to be this ... and that can take any arbitrary information about any arbitrary number of columns. And then it turns out if I look at the help information on order, what I'll see is that order can actually work on any arbitrary number of inputs here. So what this is going to do is it says order returns a permutation which rearranges its first argument into ascending or descending order, breaking ties by further arguments. So what that means is that I could then set up my more flexible function here to basically just pass along whatever inputs are given here into here. And so now, once this is now going to create an ordering vector based on whatever columns get passed in here, they're just going to get passed along to the order function, and then I can just use that for sorting by taking the data input and using this ordering vector. Okay. And then here I'm using this invisible function that I haven't really talked about, and I don't think I'll take the time to talk about, but that I can use instead of a return statement. So that gives you another example of how this ... functionality can be useful. Okay, any other questions here? Yes?
But in this solution, the order function has no information about the data. So how is it sorted?
Right, so this, so I guess I should have said that as well. This is going to require usage of this function as it's written here would require me not to give inputs that are like the indices of the columns. It would actually require me to actually pass in the explicit columns, and then the order function can then work on the explicit columns. Okay, other questions? Yes.
Sorry, could you just clarify when you say explicit columns, is that like $$ destination?
Yeah, whereas when I used this before, I had done some things like in some cases I had done things like referring to columns just by index value here, like 1 and 2.
Okay.
So I'm sort of mixing and matching here, which is why this is a little more confusing than I might have wished it would be, which is some of these functions, a function written like this will work either if I pass in col1 as an index or if I pass in col1 as the name of a column. Whereas the way that I wrote the function in the solution to be more generic in terms of how many columns it takes in, this one will only work if I actually explicitly give the entire column on which to do the ordering. There are probably some other ways I could have written this to be more flexible if I just wanted to pass in an arbitrary vector of indices. So there's a lot of different things you could do here. This is just illustrating some ways that you could do it. Okay, so let's go over to module 7. So some of the stuff in here, I think, is, if you look at it, it's basically some tools that would be useful for handling different kinds of functionality. I think if you look through it, and much of this is going to be hopefully be somewhat self-explanatory, and some of the tools may be interesting to some subset of you, and some others to some other subset of you. And given we're running a little bit lower on time, what I'm going to do is just hit a few highlights here and skip over some of the tools so that we have enough time for Kelly to talk about some of the advanced plotting before we go to lunch. So the first tool that I was going to talk about, but I'm going to skip over, is the ability to fit smooth regression kind of relationships. So I won't show you anything about how you do it. You can follow along with the code here. But just to motivate why this might be interesting, I'll just show you a plot that illustrates what you can do. Suppose that I, instead of fitting some sort of linear regression or a linear regression on the logit scale, which is what you're doing when you fit logistic regression, or including quadratic terms or things like that, suppose you think there's some underlying smooth relationship between your independent variable and your dependent y variable. If that's the case, there's some nice functionality in R for fitting basically smooth relationships. And you can fit models that give you results like this. Let me make this a little bit bigger. So this is again fitting to the airline data set. And what it's showing is you could fit a model where you fit a smooth relationship between the month of the year and the departure delay, for example. And we could estimate, for example, that the departure delays are higher over the holiday season in December, lower in the middle of the spring and the middle of the fall. We could do the same sort of thing. We could fit a smooth function of departure delay as a function of hour of the day. So this is from 5 a.m. to 8 p.m. here. And here we could learn that departure delays on average are lower in the very early morning. They rise throughout the morning and reach a peak at around, I can't quite tell what that is, maybe around 2 p.m. or something. And then they seem to sort of fluctuate up and down. So you can explore these sort of more complicated relationships between variables where you assume that there's a smooth relationship, but not one that follows some strict form like a linear relationship. And so that's quite nice. I won't go into the details of how you do it, but just to give you the idea that you can do this sort of thing. Yeah.
What's the bottom?
Oh, this is just what's called a rug plot. It just shows all of the different values of the x-axis variable. So it's almost like you're trying to show not only the relationship between x and y, but you're also trying to show almost like a histogram of the x values. But it does it by just plotting a little bar for each of the individual values. In this case, you only see a few individual bars because all of the month values are 1, 2, 3, the integer values. But the departure time values have many more unique values, so it ends up just looking like a rug. Okay. I will spend a few more minutes on distributions because these end up being used a lot, particularly when you're doing statistical stuff. So basically, R, again going back to this idea that there are particular things that R does that it does really well because of the fact that it was written by statisticians and statisticians had things that they knew they needed to deal with. R will basically handle working with all sorts of common statistical probability distributions. And it has, essentially for every distribution that it is able to handle, it has a set of 4 functions for that distribution. It has a function D that will calculate the probability density function. So if I'm writing out, if I'm thinking of a normal density, the normal density function we know looks like this. If you give the D norm function an x value, it will tell you the value on this curve. That's what the D function does. So D norm does it for a normal density. D gamma does it for a gamma density function. D binomial does it for a binomial density function, et cetera, et cetera. If I want to generate a random number from a distribution, then I'll use R and then followed by the name of the distribution. So R norm would generate a random number from a particular normal distribution. If I want to know what the probability is that a distribution random variable is less than a certain value, so this would be the cumulative distribution. So if I want to know what the probability that this particular normal distribution is less than this x, which would be the area under the curve, or equivalently, if I plotted out the CDF that goes from 0 to 1 as a function of x, either it'll calculate this area, or equivalently for a given x on this axis, it will calculate the value on this cumulative density. Cumulative distribution function curve. So that's the P function. And then the Q function, let me make this a little bit cleaner, sorry about that. The Q function is the inverse of the P function. So it calculates quantiles. So if I have a cumulative distribution function like this, here's 0, There's 1. This thing has to go from 0 up to 1. If you give me a value between 0 and 1, for example, this value here is the input, it will then calculate the value here on the x-axis that corresponds to that probability. So it's basically inverting the cumulative distribution function. So we can see that we can use these in R to get the sort of numbers that we expect from if we're familiar with working with distributions. So here we go here. Okay, so let's just show a little bit of this in action. So these first couple examples are going to be for a standard normal distribution with mean 0 and variance or standard deviation 1. And so that's the reason why I'm not providing arguments for the mean and the standard deviation, because those are just by default set to 0 and 1. So if I do p-norm of 1.96, I'm saying, what's the probability that a random normal with mean 0 and variance 1 is less than 1.96? If you've done a little bit of statistics and hypothesis testing, then you will know that that's going to be 97.5% of the probability mass, and that's what we get here. If I invert that and I say, where along the axis do I want to be in order to have 97.5% of the mass less than that, that's what Q-norm will do. And so that should go back and return back the 1.96 that I put into the p-norm, because these are inverses of each other. Questions so far?
What if I want something like not on the normal, like centered at 0 and the standard deviation of 1?
Right. So that's where we go back to this idea of having default arguments. So if I look at help on say d-norm, let's do help on r-norm. It will show me that for this whole family of normal distribution related functions, I can pass in the mean and standard deviation, or I can just let them be the default arguments. And so if I wanted to generate a whole bunch of random normals that have mean 3 and standard deviation 5, I could do something like x gets r norm. I'm going to generate 1,000 of them with mean 3 and standard deviation equals 5. And this will generate those. If I look at the mean of these, it should be around 3. If I look at the standard deviation of these, it should be roughly around 5. Which it is up to sampling error. I can do this sort of thing with other distributions. I could calculate, for example, what's the binomial density for all the numbers between 0 and 10 when I do 10 coin flips, each of them with probability 0.3 of being a success. And so I could look at that and see what that is, and these should add to 1 because these are all the possible outcomes of doing 10 coin flips. I could get 0 heads, 1 heads, up to 10 heads or successes. And we can see what these density values are. And one thing that sometimes you might want to do is if you want to get a feel for what a distribution looks like, you can plot it out easily using these densities. So for example, I can create a grid of x values between -5 and 5, 100 different values. Here they are. And then if I just want to see what the normal density looks like, I can plot as a line plot, so type equals L. I can plot each of those individual x's against the calculation of the density for each of those x's. So that is just a discretized version of what I drew on the board before of d-norm. I'm taking a grid of values along the x-axis, evaluating the curve at each of these points, and then as long as I have a fine enough grid, if I just connect those points together as lines, it's just going to look like a smooth curve. And so now I'm doing this in a vectorized way. I'm calculating d-norm on that whole vector of x's at once. And now if I plot that, I see it does indeed look like a normal distribution. I could overlay a t-distribution to get a sense of what the tails of a t-distribution look like compared to a normal distribution. And so here we see indeed that the tails are much fatter for the t-distribution than they are for the red one, than they are for the black normal distribution. Okay, questions here? All right, there are a few other examples here that I will skip over. You can also do other sorts of sampling. So if I wanted to sample a random number of values from a vector, I can use the sample function. I can either sample with replacement or without replacement. That's all fairly straightforward, and there's an example here. So for example, if I wanted to do some bootstrapping and resample from the airline data set a certain number of rows from the airline data set, I could use the sample function on a vector of 1 up through the number of observations in the airline data set. That will sample a random set of indices corresponding to rows of the data set, and then I could use that for things like doing bootstrapping. Okay. let me say a little bit about the random seed, and then I'll probably then I'll say a little bit about optimization, and then we'll go to a break. Okay, so when we're generating random numbers on a computer, they're actually not random; they are pseudo-random. And so you can think of generating random numbers on a machine as basically generating numbers in a big circle. So all of the random numbers you can generate in standard software on a machine is basically a very long sequence of random numbers. Here's one, here's the next one, here's the next one. And so when you start generating random numbers, if you start here and you generate this one, and then you generate the next one, if you were to go back and start here again, you would always generate this next one in a deterministic way. It turns out there are many of these numbers if you're using a good random number generator, so you don't have to worry very much about the fact that eventually you'll come back around and get to this place you started, because it's like you'd have to generate these for like longer than the length of the universe or something like that. But what it does allow you to do is basically make all of any simulations that you do that involve random numbers be repeatable. So it would be really frustrating if I ran something that involved generating random numbers, like a bootstrap, and I got the results back, and then I told my collaborator to do the same thing, and my collaborator, she went and did it, and she got a different result back, and we couldn't figure out if maybe she was using slightly different code. We couldn't figure out if we really had code that was doing the same thing, because of the fact that the random number generation is different and is sort of getting in the way. So basically, what you want to do to make or if you realize there's a bug in your code and you want to sort of debug your code and you want to run the code such that it runs exactly the same way every time and not have it be confounded with the random numbers changing, you basically want to do something that's called setting the seed. And setting the seed basically means saying, I want to start here with this random number every time. And that means that all the set of random numbers I'm going to use in my simulation are all of the ones that are in this set that starts here. And if I set the seed to be the same value and I do this simulation multiple times, I'm always going to use the same random numbers. I should get exactly the same numerical results out. If I'm doing a simulation on a computer where I have multiple, or I'm doing parallel processing, what I would want to do is if I'm using one core on the machine and then another processor on the machine, I would want to set the seed to be different places so that I'm not generating the same random numbers on each of the two different cores. Otherwise, I'd just be getting the same answer back from the two different cores, and I wouldn't be doing parallel processing. So for the first CPU, I would set the seed, say, to be here, and for the second one, I would set it to be here. And then these random numbers for the two different CPUs would be totally unrelated to each other. So the way that you can do that operationally in R is you call this set.seed function. So let's just go down and see that. And here I'm going to sample 10 values from indices corresponding to the number of observations in the airline data set. So you can see these are the random indices that I've selected corresponding to the rows of the airline data set. And now if I sample another 10, oops, what's that? We can see that I'm going to get yet another 10 different values, different from these first 10 values. And that's because basically I'm using some random numbers here, and then I'm doing another call to a random number generating function. I'm using the next set of random numbers here. In contrast, if I go back and set this seed back to 0, I set it to 0 up here, and now I'm going to set it back to 0 and generate those vals. What I'll see is that the new vals that I generated, starting with 4, 8, 4, 1, 2, 3, are the same up here as they are down here. So that makes this repeatable. Basically, every time I set the seed to 0, I'm going back to a particular position on this circle of numbers, and I'm just grabbing these ones over and over again when I set that seed equals to 0. So that can be very handy for controlling in a controlled way the random numbers that you're using. Any questions about that? All right, and then let's just say something briefly about optimization. I won't spend a lot of time on this, but oftentimes in statistics, but in lots of other disciplines, we need to do some sort of optimization. In statistics, that usually means finding a set of parameter values that best explain the data that we've collected, like in a regression or in some other kinds of model fitting. And R has some reasonably good tools for optimization. They're not as sophisticated as, say, the suite of optimization tools in MATLAB. Maybe not quite as sophisticated as the tools in Python, although I'm not totally sure off the top of my head about that. But for standard optimization, you can do a reasonable number of things with optimization in R. And basically, when you're trying to find the optimum point, either the minimum or the maximum of a function in R, what you basically need to do is define the function that outputs that basically outputs values that for the function, and then you need to call the optim function. So, for example, here I'm going to define a function called banana, and this function looks like this. It has a low point here and higher points where the red are. So, if I wanted to find the minimum of this function, this is a function in 2 dimensions. The function takes an x1 and it takes an x2, and then it has an output in this 2-dimensional space. The minimum is somewhere like here. So if I want to run an optimization, the way that I run the optimization is I call the optim function, I give it a starting value, a place to start. So in this case, I'm just arbitrarily saying that -2, 0 is my starting value right here. And then I tell it to optimize over the banana function. And by default, this is an R function that I defined up here. By default, what it's going to do is it's going to start at that starting value, which was somewhere over here, and it's basically going to try and explore this space by sort of proposing new values and then moving to those new values, and hopefully walking downhill until it reaches the minimum value. And so you have to start somewhere, and then there are different ways to do this operation of figuring out where to go next and how to try and walk downhill. Because of course, if you're the optimizing function, all you can know is what the value of the function is when you evaluate it. You don't know what this picture looks like. The function doesn't know what this picture looks like. And so it basically is just plugging input values in this x1, x2 space into the banana function, evaluating them, and then figuring out where to move next, and hopefully walking downhill, although not always. And so it's fairly straightforward to use, but you have to be careful and evaluate whether or not it actually seems to have converged to a local minimum. And if you have a function that has many local minima, it's not necessarily going to converge to the global minimum, which is a standard problem in optimization. So I won't say anything more about that except just to point out that this functionality exists. Okay, so let's take a break now. We'll take a break till about 11:30.